If you remember, in one of our previous lectures, we tried to transfer function for different kind of inputs. Okay, so of course we know that the most important input for a control system is the reference input, and basically what we want to try is we want to track this input at the output, or at least we want to try to minimize the error between the reference signal and the measurement E of S. And in the steady-state response analysis, what we try to technically measure and characterize is the steady-state performance of a control system based on the type of the system or characteristic of the system. But we know that there are different inputs, and these are technically unwanted inputs, such as disturbance or major noise. And it's also important to characterize a steady-state response of a system for different kind of inputs. However, unlike the classical tracking performance or response to the technical reference signal, these transfer functions and structures can depend on the topology. Okay, in that regard, I really suggest you to just find the transfer function and then technically apply the final value theorem to compute the steady state output of the system. Okay, so in this tracking performance, what we try to obtain is this. Okay, error steady state. Okay, so we try to minimize error steady state. But once we analyzing the steady state response to different kinds of inputs, if we know that we assume R is equal to 0, N is equal to 0, but instead of using this signal, we directly look at the output Y of S and we try to compute Y steady state. And what we try to obtain is, given a like step input, ramp input, and different kind of conditions, we want Y of S to be as small as possible. Okay, because we want to reject the disturbance signal or noise signal at the output under steady state conditions. This is the whole idea. Okay, so if you remember, the transfer function d of s to y of s can be written as like this. Okay, t d of s is equal to g of s 1 plus c of s, g of s, and h of s. C of s, g of s, and h of s. And if you remember from the previous lecture, this multiplication of all of the transfer function in this path is called the feed-forward transfer function. So we can write this as g of s divided by 1 plus GOL s. Okay, so what's the take-home message from here? As you can see, we cannot directly use the formulas or derivations that we obtained in the tracking performance part. So in that regard, if we want you to compute the steady state response Y of S under different kind of input conditions that are not reference input, I really recommend you to find the transfer function and apply the final value theorem. Okay, so let's solve an example here. Okay, so it's a closed-loop system we already analyzed in the previous lectures. We know, I think, steady state characteristics with respect to R of t. And now, in this problem, what we want to obtain is this. Okay, so given that d of t is unit step, okay, unit step, we want you to compute y steady state. And of course, we assume that R of t is equal to 0 because it's a single input, single output system in terms of transfer functions. Okay, so if you find transfer function from d of t to y of t, it's the first thing that we need to do. Okay, so let's do that all together. Okay, so first of all, what we can do is this. Okay, so this is d of s. Okay, that's great. So we are technically characterizing this signal, d of s. Okay, that's great. So I know that this is y of s. So this is equal to what? Y of s divided by, no, it is sy y of s. Okay, s times y of s. Okay, s times y of s. Okay, that's nice. So d of s plus this signal is equal to kp times minus y of s, so I can put minus here. Okay, so it is equal to y of s, kp times y of s minus kd times s times y of s is equal to this signal, and multiplication of this with 1 over s gives us s times y of s. Okay, that's great. So let's try to simplify it to find a better form of the transfer function, or simplified form of the transfer function. Okay, d of s is the input, okay, plus kp times kd s y of s is equal to s square y of s. Okay, so d of s is equal to, so we have minus here, so put minus here, is equal to y of s. Okay, that's great. And I think I need to also put, okay, that's great, that's everything we need. Okay, s square plus kds plus kp. Okay, that's great. So d of s, okay, y of s divided by d of s is equal to 1 over s squared plus kd times s plus kp. Okay, that's great. So that's nice. So in this problem, the exact numbers of KD, KP is not given, but we assume that KD, KB pairs can stabilize the system, or we will try to find the steady state error based on the fact that we are doing this for a KP, KD pair that can make the closed loop system stable. Okay, it's the first thing that we should remember. Okay, I think that's everything we need to know for now. Okay, and we will compute the steady state error using the fact that d of s is a unit step input. So d of s is simply equal to 1 over s. Okay, so y of s is technically equal to, okay, so 1 over s divided by s squared plus kds plus kp. Okay, so y steady state is equal to limit when s goes to 0, s times 1 over s divided by s squared plus kds plus kp. These will cancel each other, this will cancel each other, and it's equal to 1 over kp. Okay, that's great. So under the fact that d of t is equal to 1 for t is greater than or equal to 0, y steady state is equal to 1 over kp. So what does it mean? Okay, first of all, if you remember, the opponent transfer function of this system is type 1. Okay, and we know that under unit step input at the reference signal, steady state error equal to 0. But we are looking at a disturbance signal, and even if the system is a type 0, type 1 system, we cannot reject unit step input that occurs at the disturbance signal. For this reason, in order to analyze the response to disturbance signals, you should really technically analyze the problem from the first principles. Okay, so it is not 0, but at least we have a control, and it says that in order to minimize y of s, we need to increase kp. Okay, so if we analyze the problem from a different perspective, if we put a measurement error here, or if we add a disturbance here, we should obtain a different result. And in general, it's important to analyze the robustness of the system with response to different kind of inputs, both for the transients and the steady state analysis.